Hey, we're back again. Well, today's topic, which is a continuation from what we were doing last time, man, that was a lot of math last time. But today, still quite a bit of math. Same idea, looking at reaction quotient. This word quotient sounds like something that has something to do with division, doesn't it? Well, you know what? There's actually nothing to do with division here. But this idea here, reaction quotient, whoa, you have no idea how important it is. Now, so far, the reaction that we're looking at, so let's say as an example. Let's look at this as an example. We're looking at a reaction. We're looking at the fact that in the beginning, we are supplying 1.5 molar of this in the assumption that the reaction have not begun. Hence, 0 here, 0 there. But what if the reaction have already begun? Meaning that, oh wait, there's no 0 here or here. There is something. Then what do? Well, that's where reaction quotient actually comes into play. Now, the reaction quotient is the whole idea of testing. Testing to see which way is the reaction leaning towards. Is it going forward or is it going backwards? Yeah, so that's the whole idea here. Given concentration of your entity, whatever they are, is the reaction going forward or is it going backwards? Hence, this is the equation to test it all. Looks familiar, doesn't it? Now, don't worry about this T. This T stands for time, meaning that at a certain time, remember, it's all about rates. At a certain time, what is the concentration of these four entities? So, the way to calculate QC, which is reaction quotient, is the same thing as calculating KC. But after calculating QC, what you do is you will compare it with the KC value. And you would say that if QC is less than KC, the reaction have not reached equilibrium yet. Yeah, that's pretty obvious. Because let's say if KC is a certain number and QC, which whatever number it is dictated by the fact that the numerator is the product. Well, you know what? We haven't got there yet. That's why QC is less than KC. That means if you haven't got there yet, you are still trying to get there. Reaction is still proceeding forward. You are still trying to make more of these so you can get your QC to a KC. Now, what if it's the other way around? What if QC is a bigger number than KC? Well, what that means is that you're going to have a big number of these. So big that it's bigger than the equilibrium constant. What that means is that at that certain time, this reaction is probably going backwards. Because you have an excess of now these things now. I shouldn't say excess, but you have more of these things than you should for equilibrium to be established. So you're going to go backwards and kind of make more of these, make this a little less to reach the equilibrium constant. Well, what about my QC is equal to my KC? Then your reaction is at equilibrium. That's it. You clap your hands and you start to dance and you say to yourself, oh, hey, I'm there. So that's the whole idea of reaction quotient. So let's do some examples. I don't have that much example to do today. In fact, today's lesson is going to be quite quick, if you get it. So I have this reaction right here, okay? Phosphorus 5 chloride, or people might call it phosphorus pentachloride, decomposes to become phosphorus trichloride and chlorine gas. Okay? This is actually an equilibrium reaction, meaning that, hey, with enough of these, going too far away from Kc, you're going to go backwards. And let's take a look to see if this scenario goes forward or backward, okay? So let's do question A. It says if all the entity was at 0.12 molar, what direction is the reaction proceeding? Now, it really says that at a certain time, at this time, and the question never says if this is the beginning. The question never says if this is at equilibrium. It's just that at this time, all of these entity is 0.12. Okay? Is the reaction going forward or the reaction going backwards? So let's do the QC expression. So as I said, the expression here is exactly the same mathematically as calculating Kc. It's just that, Kc is given to you. It's a constant, it's the same thing. And now you're just checking to see what you're getting. So this is 0.12. This is 0.12. You're dividing it by 0.12. So, hey, this you can't get easier than that. And I hope you don't need a calculator for this. But QC is 0.12. Hey, what is KC? KC is 0.8. In this case, since QC is less than KC, okay, it looks like you don't have enough product to get it up to 0.8. Hey, continue along, boys. Continue along. Reaction is still trying to proceed forward. You're still trying to make more products to get your equilibrium constant to be 0.8. 0.2, you have a long way to go, boy. Part B. Okay, look at this scenario. Usually when you have a part B of a question like this, is going to be the other way around, but let's see if that's the case. If PCl5 was 0.1, PCl3 and Cl2 was 0.3, what direction is the reaction proceeding? Okay, let's do this. QC is equal to 0.3 times 0.3 divided by 0.1. Okay, that's equal to 0.9. Now we're talking. It seems like there's a lot of product, isn't it? Okay, not a lot, but enough, more than enough, that you went over the equilibrium constant. It's supposed to be 0.8, but now you have 0.9. That means you have a lot of these. Well, too much of these, guess what? You're going backward to make some of these back. Because the reaction is only happy when it's at 0.8. That's when it's equal. So let's write that down. Let's conclude that since QC is now greater than KC, reaction is, I guess, proceeding backward. Yeah. So in this case, the reaction will go this way. So QC is quite important. How? Well, take a look at this question. This question will show you exactly why QC is very, very important. Because knowing which direction you're going will actually tell you how to set up your ice table. Let's do this. Part A. Calculate the concentration of all entity at equilibrium if 4 molars of each were initially given. So here's my situation here. Here's my situation. Here's my ice table. It was said that 4 molar of each were given initially. Okay? Now, here's the problem. We don't know if this reaction is going forward or if the reaction is going backwards. Now, you may be thinking, does it matter if you're looking for the next line? Yeah, totally matters. Because if the reaction is going forward, yeah, it'll be like what we were doing before. Negative x, positive x, positive x. But what if it's not? What if the reaction is going backwards? If it's going backwards, you're going to get less of these and more of these, so the situation kind of reversed from what we are used to. That will totally mess up what you will do. So which way is it? Well, the only way to know is to actually check. Let's do a QC check. You guys probably didn't get the joke. QC check, quality control. You guys too young to know anything about quality control. Hey, this is a good one. Okay. As you can see, these guys are not aqueous. Okay, these guys are all gases. Because of that, water is actually part of your equation. Okay, so hey, that's pretty crazy to see that. Oh yeah, and I noticed that you put water here. We never put water there. Well, we can't put water there now because these guys are all gas and not aqueous. So I wonder if anybody remember that. All right, so let's plug that in. 4, 4, 4, 4. Again, hopefully you don't need a calculator for this because QC is equal to 1. Well, if QC is equal to 1, it is definitely less than KC. That means you haven't got here yet. You get it? At this point, when they're all 4, 4, 4, 4, that's a situation where you did not reach equilibrium yet. Nope, you're still quite a long way to go. So what does that mean? That means reaction still proceeding forward. That's what it means. So you're going to do exactly what you've been doing. There's still going to be less and less of these. And of course, there's going to be more and more of these. All right, so at equilibrium, it's going to be 4 minus x, 4 minus x. So the other should be 4 plus x and 4 plus x. Okay. All right, so let's do the math. Your favorite part. So your KC expression, okay, it's going to be CO2 times H2 over CO times H2O. KC is given to be 4.2. This is going to be 4 plus x over 4 minus x, 4 minus x. Okay, that's should be simple enough for you to do. I'm not going to do this here because it's going to take too long. I don't want to spend too much time on algebra. You know I'm good at algebra. Actually, I suck. I already did this earlier. So x is 1.38. Oh man, I hope I'm right. So all you have to do is plug them back in. So carbon monoxide is equal to water, which is equal to 4 minus 1.38. That will give you 2.62. Makes sense. And CO2 is equal to H2, which is of course 4 plus 1.38. That is 5.38. Again, it makes sense. Okay? If you take these number and plugged it in back into your QC equation, you should get 4.2. Which means you're doing great. You're doing so awesome. So awesome that I want to be your friend. Alright? Hey, hopefully you're taking this down, eh? Because I'm going to take this down. And we're going to do part B. So let's take a look at part B. Nope. Part B. So let me erase all of this. Hopefully you understand it. And let's take a look at part B. Pretty sure it's the other situation. It's always like that. Let's use red. I like red. Red's one of my favorite color. Alright. Oh, let's erase these two. They're not going to be 4 anymore. Part B. Calculate the concentration of all entity at equilibrium if CO and H2O was initially given as 1 molar. Okay. CO2 and H2 was given as 3 molar. Sure. Alright. If you are given the product to be something, unless they say that these are 0, you don't have to check QC, because if these are 0, you know the reaction is going to go forward. But if they give you something for product, you're going to have to test, because you don't know if this is enough or too much. I don't know. It might go backward. So let's test. So you're looking at 3 times 3 over 1 times 1. And the answer is 9. Hey! QC is bigger than KC. That means there's more of these than it should be. And if that's the case, you better go backward and make some more of these. Right? Because what you want to do is always satisfy KC. The equilibrium constant is the most important thing. Okay, you have to satisfy this number. Right now, you went over. This is too much. So in this case, you're going back. You're going back. Because you're going back, these are the ones that are going to be negative an x. Oh, I wonder what that was. Huh. And for these will be positive x. Because you're going backwards, you're going to make more of these. Makes sense, right? So at equilibrium would be 1 plus x, 1 plus x. This would be 3 minus x, 3 minus x. Okay? So let's do the equilibrium expression. So 4.2 is equal to 3 minus x times 3 minus x over 1 plus x over plus times 1 plus x. Okay? Hopefully you guys can see that this is this, and then this, and then this. X is equal to 0.31. I did this ahead of time. Hopefully, as I said, I'm right, or else it'll be pretty embarrassing. Now you can just plug in it. CO is equal to H2O is equal to 1 plus 0.31. Hey, CO and H2O is 1.31. Whereas CO2 is equal to H2 and it's 3 minus x. So in this case, why did I write x? I know what x is. Why do I write x? And it's going to be 2.69. Again, a way to check is to plug these numbers back into your QC expression and see if it equals to 4.2. Very important. So make sure you keep that in mind, that if they give you some sort of concentration for product, you know that these are not zero. If these are not zero, it doesn't necessarily mean these are going to be negative x. As you can see in this situation, no, the roles are reversed. These are going to be negative x, and these are going to be plus x, because you need to find out which direction is your equilibrium pointing to. All right. As I said, this is going to be a shorter lesson for the day. I do have a few more questions that I want you to do. And hopefully you're able to do them and understand them all. All right. Let me get out of here and leave you guys alone now. Bye now.